one-field sequence motor with double three-phase one-state in the stop and low-speed driving. Now let me begin with the introduction. As you know, electric vehicles and hybrid vehicles are gaining popularity. However, from the viewpoint of cost, the ICE vehicles are still mainly used, and the improvement of the ICE vehicles' fuel efficiency is an extremely important issue. To realize and to improve fuel efficiency, the technology using alternator, which is mounted in ICE vehicles as a motor to start and assist the engine to realize the improvement of fuel efficiency, is attracting attention. This type of alternator is called ISG, and using ISG to assist the engine is gaining popularity. To control ISG, the position sensor is generally equipped, but using the position sensor will increase the whole system's volume, cost, and reduce the reliability. The position sensor control method for ISG is expected. The type of ISG has many types. So I'd like to introduce the fear of target ISG to be controlled in this slide. The structure of target ISG is shown in this figure. The rotor is one field type, and the magnetic flux is generated by electromagnet in it. The stator has two sets of three-phase winding and has 30-degree phase difference between each other. This type of ISG is called a one-field sequence motor with double three-phase stator in the sense of electrical machines, and it is our target motor to be controlled. Because there are two sets of three-phase windings, there need two sets of inverter to operate the motor. And because the rotor is one-field type, the magnetic flux from rotor is variable. And because due to stator has two sets of three-phase windings and has 30-degree phase difference, the sixth harmonic from the power converter will be reduced. And what's more, target motor can be operated even if one of the inverters is broken. Since the target motor has special structures, I'd like to introduce the fear of target motor from the viewpoint of sensors control. The control system for the target motor is shown like this figure. There is two current controller to control the A set and B set current. And because the rotor is one field type, they also need a current controller to control one field current. We'll be using a position sensorless control method, high frequency in single injection method at stop and low speed driving. We usually inject the high frequency voltage to the target motor and extracting the information from high frequency current flow out from the motor. In the case of target motor, there are three places to inject the signal and three places to demodulate the signal. So the target motor has a lot of operation items and has a high flexibility for control. Thus, the target motor is very interesting as a control object. But the ballistic sensorless control method for the target motor has not been examined yet. So our purpose for research is the realization of the position sensor control for the one-field sequence motor with double three-phase one state in stop and low-speed driving. To realize the purpose, we first examine the feasibility of the existing sensor control method when applying to the target motor. And the examined result will be explained by these three steps described here. First, we show the model for the target motor and derive the high frequency current equation used for the position estimation. And then we examine the feasibility and conduct a study on problems when applying the existing sensor control method to the target motor. And finally, we propose a method to solve the problem and using the field of the target motor. Now let me introduce the model of the target motor. The equivalent circuit on DQ axis is shown in this figure. In this figure, the resistance is omitted but defined in this table. The self-inductance in each magnetic interference will occur between each set. So we need to define the mutual inductance between each set. And the dx is inductance is defined as d. Qx is mutual inductance defined as q. And the mutual inductance between stator and rotor is defined as fa and b. With these parameters, the motor model on dq axis can show by this formula. On the right side, and the second term on the right side of this formula is represent the voltage drop due to the inductance. And the third term is the armature reaction. Because the magnetic interference, the motor model is very complicated. But with this motor model, we can derive the equation for high frequency current, which is used for the position estimation. And the derived result is shown in this slide. High frequency equation on estimated coordinates gamma delta x's is shown in this formula. K1 to K5, A, B are parameters defined anew from the motor parameter, and the delta theta is the position error. With this formula, when injecting voltage to the motor, the high frequency current can be calculated. And the key of the formula is that within the same color of frames, the elements match exactly. Thus, the formula shows symmetry. Based on the high frequency equation, the feasibility of the existing sensorless control method can be examined. For example, when we injecting high frequency voltage, both formula can be expressed by this equation to the target motor. The high frequency current in each set could be calculated and expressed by these equations. From the high frequency current, from the equation, we can confirm that in each set, the high frequency current can include the position information, and anyone could be used to estimate the position. But from the viewpoint of easy to use, the position information could be easily taken off from I delta A, I delta BH, and IFH, and three of them could be used to estimate the position simply. To confirm the formula is correct, we conduct a simulation. This simulation is to confirm the high frequency current in each set contain the position information when using an existing method. In this simulation, we inject the sine wave voltage with the amplitude of 2 voltage and 2 volts and the frequency of 500 Hz to the A set gamma axis, and then change the position error delta theta from -pi to pi to observe the wave of high frequency current in each set. The simulation block diagram is shown in this figure, and the simulation result is shown in the left table and left figure. From first line to the last line is respectively denotes the position error, high frequency current in A set, B set, and the mono field. From the simulation result, we can confirm the current amplitude change following the delta position error delta volume, and the simulation result is matching with the equation. Based on this simulation result, we conduct position sensorless simulation to evaluate the performance of the position sensor control using the existing method. We inject single to A set gamma axis and use A set to delta axis high current to estimate the position. The simulation block diagram is shown here, and the simulation condition is shown in this table. The DC link voltage is 12 volts, and the field current is 4 ampere, and then we give 100% throughput to the target. The simulation result is shown in this figure. From first line to the last line is respectively denotes the current in A set, B set, the real position theta, estimated position theta part of the delta theta. When we change the control method to the sensorless control, we can know that the estimated position theta hat tracking with the real position theta and is approximately equal. And even we give 100% truth to the target monitor, and the control system is steady. So the results show that using existing centralized control method called realized position centralized control for the target monitor. But using the existing centralized control, we have a program, and I will explain the program when you use this figure. When we give 100% truth to the target monitor, a large total ripple is generated, and it's about 9% of the radial output torque. And this torque is bigger than the case of PMSM, and will have influence on the motor drive. So the reduction of the ripple is desired. To reduce the torque ripple, we first analyze the cause of the torque ripple and then propose a reduction method. Now let me explain the cause of the torque ripple. The torque can be obtained by calculating the outer product of magnetic flux phi and armature current I, which are orthogonal to each other, just like this equation. In the case of PMSM, the value of I will oscillate because of the high frequency current, but the value of phi is constant. So the torque ripple for PMSM is relatively small. But in the case of target monitor, the value of phi and I will oscillate together because of the high frequency current, and consequently generate a large torque ripple. So to reduce the torque ripple, making IFH equal 0 to stop phi's oscillation is most expensive. Based on this theory, we propose the method. The proposed method uses the fear of the target motor. And because of the target motor has several places to inject the signal, we inject signal to B set and B set at the same time. And the signal injected to B set have opposite sign to A set, just like in this figure. And due to the formula for high frequency current shows symmetry, the proposed method could make IFH equal 0. To confirm the theory is correct, we conduct a simulation. When injecting high frequency voltage to the target motor's A set and B set at the same time, the current can be calculated and the equations calculated in here. And the simulation result to observe the high frequency current's amplitude is shown in this figure. From the simulation result and the formula, we can confirm that I delta H, I delta BH include the position information and can be used to estimate the position. And the proposed method would make IFH equal 0, and due to IFH equal 0, the phi's value becomes constant, so the torque ripple can be reduced. Based on this experimental result, we conduct position sensor control using the proposed method. When we change the control method to the position sensor control, the estimated position tracking with the real position and is approximately equal with the real position. And you can give 100% torque to step to the target motor, and the control system is steady. And then we observe the torque of when using the proposed method, and the result is shown in this figure. From this figure, the torque ripple can be largely decreased when using the existing method. So using proposed method not only can realize the position sensor control, but also can reduce the torque ripple. And the conclusion. Target motor is one field sequence motor with double three-phase one stator, and for purpose of research is the realization of the position sensor control for the target motor in stop and low speed driving. To realize the purpose, we first show the model for the target motor and derive the high frequency current equation used for the position information. And then we discover the position sensor control can be realized by using the existing method, but a large torque ripple is generated. To reduce the torque ripple, we propose a method by injecting signal in two sets of windings to realize position control and reduce the turbulence. Thank you.